Hello everyone, welcome back to the lecture series on Foundations of Deep Learning, Concepts and Applications. In your previous session, you have gone through the fundamentals of convolution neural network, and finally you have built up a convolution neural network from the scratch in your hands-on session. In today's session, we will introduce you to some standard CNN models. The contents for today's discussion is architecture and implementation of a standard CNN model called as AlexNet. Now, just a quick recap of what convolution neural network structure looks like. So, we have an input layer where we give the input image, then we have the convolution layers, pooling layers and the fully connected layers, and finally the output layer. Convolution and the pooling layers, they help in the feature extraction, whereas your fully connected layers, they help in the classification task. Now, that is the fundamental structure of any CNN architecture. Standard CNN models are the architectures which are known for their application in image recognition problem. Now, we will see what is there in a standard CNN architecture. Now, we will start with a little bit of a background. What was there in computer vision field, what was happening around the year 2000. So, before 2012, from 2000 to 2012 say, or from the beginning of 2000, computer vision relied heavily on handcrafted features. So, around 2000, scientists wanted the machines to see as human, but machines could see, but they were not able to see as humans see. So, they were recognizing patterns, they were recognizing some edges, some corners, but not an object as a whole, because they heavily relied on handcrafted features. Now, what are these handcrafted features? These are manually defined a set of features, and those features were extracted. Example, edge detection, corner detection, histograms, etc. And handcrafted features relied heavily on human intuition. The designer must decide which features are important. So, basically, these handcrafted features, or what required human intervention, that that was giving a limitation to the extent how computers can see objects. What are the limitations? Works well with simple tasks, but struggled with large complex data sets due to too many variations, different lighting, poses, backgrounds, and also can't capture higher level patterns of cat class or dog class, etc. So, it was handcrafted features worked well with very simple tasks, but when we wanted the machine or computer to recognize a cat as a cat, it was not able to do that one. So, these handcrafted features actually they were based on some algorithms called shift, hog, etc. algorithms, and due to this limitation, scientists were not able to move further in the computer vision field. Then what happened is, in 2009, a big massive data set was created. This was also a problem that the scientists felt, that when they tried the machines to see the images as humans see, the problems that came into picture were these neural networks, they required a lot of images which was not available that time. Also, the neural networks were slow and it hampered the performances. It was very long and lengthy process. Then in 2009, ImageNet dataset came into picture. So, you can see this is a snapshot of the ImageNet dataset, which have 1.2 million high resolution images. And these images, this dataset was created by Fei-Fei Li from Stanford University in 2009, and it had 1,000 categories of images, and it took the motivation from the WordNet. What is WordNet? We will see. WordNet is a large lexical database of English. Sync sets are a group of cognitive synonyms of nouns, verbs, adjectives, and adverbs, and each sync set expresses a distinct concept. Basically, from all the words, whatever images they can generate, all those images were there in the ImageNet dataset. And it has 1,000 categories of images, and it became the benchmark dataset for any object recognition problem. So, at least one of the problems got solved in 2009, where with the ImageNet dataset coming into picture. Now, we will come to a competition, ImageNet Large Scale Visual Recognition Challenge. This was a competition which was running annually between 2010 to 2017, and it was a benchmark competition in computer vision field. Okay. It was designed to measure the progress of algorithms in recognizing and understanding objects in images on a large scale. So, that was the main intention for this competition. The best model at that time could barely reach 74% top 5 accuracy, which means if the computer or the algorithm is trying to guess the image, what the image is of, then 26% of the time it was making mistakes, okay, among the top 5 guesses. So, your model will predict 5 times what is the image about. So, the top accuracy that was achieved that time before 2012 was around 74%, and 26% times it was giving errors. Then came a picture where Alex Krzyzewski, Ilya Sutskever, and Jeffrey Hinton from University of Toronto trained a deep convolution neural network using GPUs on ImageNet. So, they wanted to use the ImageNet dataset, or they used the ImageNet dataset and train the neural network in GPUs. Okay, we will see how brilliantly the training has been done, and they wanted to check how this deep convolution neural networks can they achieve or go to a place where the computers can see images or recognize images as human beings. And this deep convolution neural network, they named it as AlexNet. Now, we will see what is this AlexNet. AlexNet is a deep convolution neural network consisting of 5 convolution layers, 3 max pooling layers, 2 fully connected layers, and 1 softmax layer. It is used for image classification task. Now, what is the function of convolution layer? It extracts the patterns in images. In each layer, there are multiple filters. Each filter will give one activation map or feature map. Then there are max pooling layers. We know max pooling layers are used for dimensionality reduction, and it removes unwanted information. Then comes the fully connected layers with ReLU activation function. These are basically multilayer perceptrons, and they are responsible for learning high-level representations and making the predictions. Okay. Then comes the softmax layer, which classifies the image into 1,000 classes. So, now we will see how the entire AlexNet architecture looked like. So, we have the input layer where we put the input image 224 cross 224 cross 3. It is an RGB images, so we have the 3 channels. This goes to the first convolution layer or conv1, which is also having the ReLU activation function. The conv1 is having 96 filters of size 11 cross 11, stride 4 and padding 0. The output size that is coming out after this conv1, the output feature map size is 55 cross 55 cross 96. And how we are calculating the output size? We have the formulas here. You all have seen it before also. So, the height of the output feature map is height of the input feature map minus the kernel size or the filter size plus 2 padding divided by the stride plus 1. Similarly, the width output width of the feature map equal to input width minus kernel size plus 2 into padding divided by stride plus 1. Once we get the output from conv1, it goes to the maxpool1 layer of size 3 cross 3 and stride 2. And maxpool layer, what it does, it reduces the spatial dimension. So, the output dimensions become 27 cross 27 cross 96, and 96 comes from the number of filters in the previous layer, conv1 layer, and it downsamples the image. Okay. Then this output goes to conv2 plus ReLU. So, this convolution to this layer, it has 256 filters of size 5 cross 5, stride 1, padding 2, and output size of the feature map generated is 27 cross 27 into 256, because the same spatial dimensions are kept as maxpool 1 and 256 comes from the number of filters that are there. It captures mid-level features like shapes and corners. This output goes to maxpool 2, once again size 3 cross 3, stride 2, padding 0, and output size, it reduces the spatial dimensions to 13 cross 13 and number of channels become 256 because that is the number of filters that was there in the last layer. Once again it reduces the dimensionality. Then we go to conv3, which is also having ReLU activation. Conv3 is having 384 filters of size 3 cross 3, stride 1 and padding 1. We'll come to the output a little later. We will see conv3 and conv4 are exactly same, convolution layer 3 and 4 are having same parameters like 384 filters of size 3 cross 3, stride 1 and padding 1. And both of these gives the output feature map size as 13 cross 13 into 384. 13 cross 13 comes from the maxpool 2 output spatial dimension, 384 comes from the number of filters, and then it goes to convolution layer 5 plus ReLU. Convolution layer 5 have 256 filters of size 3 cross 3, stride 1, padding 1, and the output size becomes 13 cross 13 into 256, and this level captures the final level features. After this, the output of convolution layer 5 goes to maxpool 3, where the spatial dimensions are reduced to 6 cross 6 and the number of channels is 256, and this goes to the fully connected layer, which is having 4096 number of nodes. Then the output of this fully connected layers goes to the second fully connected layer, again having node number 4096, and then it goes to softmax, which is having 1000 channels. So, when the output of maxpool 3 is going to fully connected layer 6, which is having 4096 neurons, the size that is going to the, after flattening, the size that is going to the fully connected layer is 6 cross 6 into 256, which is equal to 9216, and this goes to the fully connected layer. We will see it when we are doing the parameter calculations as well. So, this is the overall architecture of AlexNet. Now, in my previous slide, I was telling that mid-level features, high-level features. So, we want to see what are the types and characteristics of image features. So, in an image there can be low-level features, mid-level features and high-level features. Now, what are these low-level features? Low-level image features include the color, the text, shape, edges and corners, which are extracted directly from pixel values or small group of pixels of an image. Whereas your mid-level features, this describe a large pattern or a structure that emerges from a combination of low level features. 2 or 3 low level features combined together will give you a mid level feature. They often represent parts or shapes, but they do not represent the full object. High level features, these correspond to the object level representation, like the cat representation, the cat class or the dog class in an image. So, this is an example of a feature of features in an image. We see in the low level features we have edges, dark spots that are there. In the mid level features we have ears, eyes, ears, nose, and in the facial high level features we have the complete structure of the face. Okay. So, if my image is of a human face, low level features will take out or extract only the edges, dark spots. Mid-level features will extract a part of the face, that is the eyes, ears or noses, and high-level feature will give the entire facial structure. Now, we have seen AlexNet have a lot of convolution layers. We will try to see how the parameters, number of parameters are calculated in each layer of AlexNet, because the number of parameters decide how much computational power is required. So, in convolution layer 1, we have 96 filters of size 11 cross 11, and if we do the calculation, so the number of parameters are calculated like 11 cross 11 into 3. This 3 comes from the RGB image input, because it is having 3 channels, and into 96, 96 comes from the number of filters, okay, and which turns around to 34,944, which is around 35,000. Then convolution layer 2, it has 256 filters of size 5 cross 5. If we do a similar calculations, we get 614,656 parameters. Convolution layer 3, we have 384 filters of size 3 cross 3, and if we do the calculations, 3 cross 3 size into 256 number of filters plus 1, this one term comes for the bias term added for each filter into the total number of filters, which is nothing but 384, and that is around 885120. Convolution layer 4, 384 filters of size 3 cross 3 are there, and if we do the calculation, it is 1.32 million parameters. And convolution layer 5, similarly 256 filters of size 3 cross 3. If we do the calculation, we get 8.84 million parameters. So, this table gives a comprehensive picture of the number of parameters that are there in each and every layer of convolution, each and every convolution layer of AlexNet. Then we will see the parameter calculations for the fully connected layers. Now, fully connected layer 1, there are two fully connected layer 1. Input size is 9216. This is what I was telling. The input size is coming from the max pool 3 layer, which was having 6 cross 6 into 256. That was the size. And if you flatten it, the input size becomes 9216. Which is 6 into 6 into 256. And the number of nodes in the fully connected layer, the first fully connected layer is 4096, which is, this is shown as FC6 in the picture that I have shown in the AlexNet architecture. And if we do a parameter calculation here, we see 37 million, around 38 million. In the second fully connected layer, we have number of nodes is 4096 once again, and the parameter calculations gives me 16 million parameters. Then we have the softmax layer, where the number of channels is 1000, and if we do a parameter calculation, that is number of nodes into the number of output channels plus the output channels together, it gives 4097000 or 4 million parameters. Okay. So, if we see in each of these fully connected layers, the parameters are in millions, okay, whereas in the convolution layer, in the first few convolution layers, they were in thousands. So, if we see the AlexNet architecture, the total number of parameters are 62.4 million parameters. And if we carefully see, 95% of these parameters are coming from the fully connected layers. So, my fully connected layers are the ones which are having the maximum, that is the maximum dense part, and which is taking the maximum compute power, because there we have the most of the parameters are there in that portion of the structure. Now we will come to how efficiently and brilliantly that AlexNet has been implemented. So, AlexNet is a big structure. It's a deep convolution neural network, and if we try to train it in CPUs, it would take it will take months. So, what this team of scientists did is they first trained with 1.2 million images from ImageNet dataset, and then they trained with stochastic gradient descent with momentum, where the beta value they chose as 0.9 and a batch size of 128. And then what they did is they used two NVIDIA GTX 580 3GB GPUs for training, and they used these two in parallel. What they did is they have splitted the model across the two GPUs. The half of the kernels were sent to one GPU, another half of them were sent to the other GPU, and this had a very good improvement in the time. That means it has sped up the process. So, they have made the training in such a way that the training time was only 5 to 6 days, and they trained the model for 90 epochs, and they did data augmentation was done, like cropping, flipping, color jittering, with a dropout of 0.5, 0.5 probability were used. These were used to prevent overfitting. So, this is the implementation details of AlexNet. One of the very important significant point to be noted here is the use of two NVIDIA GTX 580, only 3GB GPUs, and they have done it in a parallel way. Both were running parallelly, and that has sped up the process very significantly. So, this is one of the inventions of AlexNet. And another innovative approach in AlexNet is it used ReLU activation functions to mitigate the vanishing gradient problem. So, previous to AlexNet, models were using activation functions like sigmoid and tanh, but that was leading to something called as the vanishing gradient problem, which is the case that let me tell you what exactly is the vanishing gradient problem in a very simple way, simple terms. Vanishing gradient problem is during the backpropagation, we propagate the gradients from the last layer to the inside layers, or from the output region towards the input region. And if the gradients are small, we have seen during the backpropagation, the gradients keep on multiplying, and if one small factor gets multiplied by another small factor, it starts vanishing, it starts decreasing, and this leads to, if the neural network is very deep, it leads to vanishing gradient problem, and when vanishing gradient problem occurs, the weight updations stop. So, this stops the training of the algorithm. When sigmoid or tanh activation functions were used, vanishing gradient problems were coming into picture, but scientists of AlexNet team, they used ReLU activation function to mitigate this vanishing gradient problem. Okay. Now, we will come to the ImageNet Large Scale Visual Recognition Challenge 2012. So, I told in the beginning of my presentation only that it is ImageNet Large Scale Visual Recognition Challenge ran from 2010 to 2017, and we will see what is the picture at 2012. In this competition in 2012, AlexNet achieved a top 5 error rate of 15.3%. That means only in 15.3% of the cases, your top 5 guesses about the object, what the object is, or what the input object is, only in 15.3% of the cases it turned out to be, the prediction turned out to be incorrect. Whereas in almost 85% of the cases, it predicted the correct object. So, this is more than 10 percentage points better than the next best competitor at 26.2%. So, it was a quantum leap. So, it was a huge improvement over prior models which relied on shallow learning and handcrafted features. So, this became such a leap, and it was almost it's the starting era of deep neural networks, deep convolution neural networks for image recognition problems. The success of AlexNet inspired models like VGGNet, GoogleNet and ResNet. In succession to AlexNet, people started working in that same direction, scientists started working in that direction, and these inspired models like VGGNet, GoogleNet and ResNet. And VGGNet and GoogleNet we will study in my next session. This is the reference, the original paper by Krzyzewski, Alex, Sutskever, Ilya and Hinton Jeffrey on ImageNet classification with deep convolution neural networks. I urge all the students, participants to go through this paper. So, to summarize what we have seen in our today's session, we saw that around 2000, in the year 2000 to 2010, there was kind of a AI winter where not much of things were happening in the computer vision domain because of two major limitations. One is the dataset limitation, another one is the computational power limitations which was there, and people wanted machines to see how humans see, but that was not happening. Machines were able to see small features, small portions of an image, but it was not able to recognize any object. Then in 2009, Fei-Fei Li at Stanford University, they came up with the ImageNet dataset with 1.2 million high resolution images of 1000 classes or categories, and this helped to solve the problem of large dataset availability. Once the datasets came into picture, then a group of scientists, Alex Krzyzewski and Ilya Sutskever and Jeffrey Hinton, they started training a deep neural network, deep convolution neural network for image recognition problem. And the structure of this deep convolution neural network that they designed is having 5 convolution layers with ReLU activation function, with 3 max pooling layers and 3 fully connected layers, the last one being the softmax layer, which is for classification task. Then they trained that entire thing on the ImageNet dataset using a stochastic gradient descent with momentum algorithm, and one of the most smart way of implementation is they used 2 GPUs in parallel for the training purpose. How they use the 2 parallel GPUs? They split the model into 2 parts. Some of the kernels went to one GPU and the others went to the other, and the second one, and which have really speed up the process of training. The training got completed in only 5 to 6 days. And then they have used ReLU activation function other than or unlike the previous ones which used sigmoid or tanh activation function, and ReLU activation function helped to mitigate their problem of vanishing gradient problem. And then in 2012, the ImageNet large scale visual recognition challenge, that is where AlexNet showed its performance, brilliant performance. It was a quantum leap from the other models that were there. It went to the top 5 error rate of 15.3%, which is 10 points higher than the best model that was there. So this was a quantum leap in deep learning or deep neural networks, and the success of AlexNet have inspired more standard models like VGG models and GoogleNet, ResNet, which came in the successive years, and it has changed the entire era of computer vision. So with this one, I conclude today's session. I hope you have found this session informative, and please go through the original paper that I have shared in the reference, and till we meet for the next session, thank you and happy learning.